Okay, so, okay, that works. So just as a reminder, I'm sure you're well aware, tomorrow's the midterm, 6 to 7:30, and I have tried to put everything together in terms of what we will be giving you. As a reminder also, we will provide the aid sheet that I have sent around, and you do have the option of doing your own aid sheet. So both of those can be done or can be used on the exam. The room assignments are already done. I don't think there's anything else on that. Yes, room assignments. So what we have completed thus far is everything up to Chapter 5, which includes dimensional analysis. And the next two chapters, Chapters 6 and 7, really are very specific use cases of interest to mechanicals. And the other thing is the application of a lot of the ideas that you have already developed in Chapter 5 and some of that intuitive / physics that you were applying in terms of getting things together. Yeah? Okay. Okay. It's not working. Piping is really important to us. Given a pipe geometry, fluid properties, and a desired flow rate, what pressure drop is necessary to drive the flow? That determines pumps, whatever else you're going to put into the system. Given the available pressure drop from a pump, what flow rate can be achieved? And we have to understand more of the nature of the flow. And just as sort of advanced discussion point, I am looking at different ways of approaching these problems. Not tomorrow for you guys, it's on Thursday. On Thursday I'll talk about different approaches, but our main focus will be Moody chart. But one of the problems with sort of making these statements here in this slide, laminar flow, smooth and steady, low Reynolds number, viscous forces are dominant, predictable layered motion. Turbulent flow, fluctuating and agitated, high Reynolds number, inertial forces, and chaotic random motion. You and I will all have different pictures of that. We will understand that differently, and we will not. So in this course, I will never tell you anything about transition because I'm afraid of trying to describe it. It's one of the more difficult things that we do in fluid mechanics is the transition between laminar and turbulent flows. But if I'm measuring something within a pipe, so if you can imagine, I have a pipe, and within that pipe, I put some sort of ideal probe. So somewhere in there, and that probe is able to measure velocities at that location. If it's a laminar flow, the measurement that I'll get will look something like A. That is steady, no changes with time, nothing happens. When it transitions, the laminar flow will see sort of bursts of turbulence. Those bursts will look like that kind of signal. Again, I'm just measuring at that red dot in the flow. And finally, I'll have a non-repeatable continuous turbulence that occurs at high Reynolds number. And the turbulent flows fluctuations are random, cover a wide range of frequencies. Yeah, sure. And that's kind of a good definition of it, but maybe this is a little bit more helpful. So when I look at these flows, this is the difference between laminar on the left and turbulent on the right. You'll notice that if I look at that flow, I can put a light on behind it and nothing sort of shadows, it just keeps repeating. And if I do a long exposure with a camera, what that does is it allows me to take an average. And that average would look something like that. It won't look like this. This will be an instantaneous plot or picture, and that instantaneous picture gives me a slightly different view every time I take it. So for flow in circular pipes, and I think I kind of made a mistake on the aid sheet that I'm going to regret, but I'm going to say 2300, 2100. So the numbers, that number is going to be a number that really varies from problem to problem, but you can see the first application of this dimensional group, this really important dimensional group for you, of Reynolds number. So Reynolds number based on diameter is rho v diameter over dynamic viscosity, or viscosity, and you have for a 5 centimeter pipe at 20 degrees C, you can see what the differences are. So you transition to turbulence at 0.7 meters per second for air and 0.05 meters per second for water. And that's the difference in viscosity. That's the only thing that's making the difference between, well, viscosity, if we went with kinematic viscosity, it's a bit easier. I would just have one term. But rho and mu are the things that are driving that. Velocity and diameter are the same both in the air and water flow. If you are interested, there are a lot of pictures on various image searches looking at the Reynolds pipe experiments. But Hagen back in 1839 and Osborne Reynolds in 1883, and Reynolds in 1883, that's the fundamental paper. You can actually download it. And it's, I believe it's a Proceedings of the Royal Society. It's one of the good things about current backups is that a lot of the more interesting papers and fundamental papers have actually are now available online. So Hagen introduced 2 regimes of viscous flow from experiments on water and brass pipes. So it deduced for Reynolds number that the pressure drop is proportional to velocity, and for a turbulent regime that it went as 1 3/4, v to the 1 3/4 for that pressure drop. Everybody's worried about pressure drop. We're not worried about velocity so much. Showed the change depended on the dimensionless parameter, which is now the Reynolds number, so you see where it comes from. And visualized transition using a dye streak. And this was really kind of clever and difficult at the time. You have a small needle over here, you have a tank, you inject the dye in there, and with very, very, very primitive equipment, got some pretty good shots to show what the flow looked like in laminar cases versus turbulent. And this is something that, quite honestly, has kept a lot of researchers busy for a number of years. And you've talked about this, and I think you've talked about this already, where you have these entrance regions. So I have a flow that's coming in, say from a tank, it's driven by pressure, and the initial velocity profile, as it enters at that point, is going to be 0 at both of these walls and a maximum at the center where it's not affected by the wall. And then it's going to move downstream. And you'll notice that there's a small layer that grows, and the boundary layers, as the flow sort of moves downstream, expands until you get, for laminar flow, a laminar profile. And a laminar profile is there. So I'm going to say U sub r. And so you have something that looks pretty bad, an entrance pressure drop, and then a recovery. And then finally, it goes to a linear pressure drop as soon as you have the fully developed regions downstream. And a lot of what we'll talk about in these next sets of lectures is how to define this pressure drop, how to define what's happening in terms of the entrance length, and then finally how to deal with the linear portion of that. So the entrance length for And I don't want to do that. The entrance length, L over D. So again, another dimensional group that you've already calculated when you looked at all of these different cases. If you have a Reynolds number based on diameter, you'd have a L over D that's about 0.06 Reynolds number for laminar flows. And for turbulent flows, you kind of have an entrance length that's not that. It's Reynolds number based on diameter to the power 1/4 at times 1.6. And for most engineering applications, pipes are very long, length over diameter greater than 1,000. In those cases, entry length is a small fraction of the total length. And we can assume that the entire flow is fully developed. And we generally don't sort of do anything specific on entry losses. We just sort of say there's an entry loss here, and we don't worry about how long that takes in reality. So the energy equation doesn't really change very much. We just sort of say, hey, we have a pressures at the initial point over here. That's 1. And we have an exit pressure of 2. And in between there, we have a velocity profile. We can look at the shear stress. We can introduce all sorts of things. But what we really care about is what's happening between 1 and 2. And those are the important parameters. We've already looked at all of those. So if we've measured them, the head loss is just going to be Z1 minus Z2 plus P1 minus P2 over rho G. And velocity disappears, of course, because it's fully developed flow. And if it's fully developed flow, velocity 1 equals velocity 2. And that head loss is the drop in the hydraulic grade line. So you've done, again, you've kind of looked at these energy equations. You've looked at modified Bernoullis and all sorts of approaches to sort of describe the same thing. Now, if you kind of look at that shear stress at the wall over here, we can do that and say that H sub F is 4 times wall rho G D. We can say the head loss is just going to be 4 times the shear stress at the wall times the length divided by weight divided by diameter. And we want to define this as a friction factor. So we want to go as HF is equal to F L over D V squared over 2G. And go ahead. Alpha is just a ratio in case there's an, say, an area change or something of that nature. Or a temperature change. So we suddenly end up with this one factor F. And that's what's going to drive the next 5 lectures in terms of how we describe things. So for fully developed flow, laminar flow, then your head losses can be solved for because we have a solution. So you have an exact solution for Poisson flow, which is flow between two between two walls. And if you solve through for all the terms, calculate what the pressure drop has to be, you end up with a term 32 mu LV rho GD squared. So diameter, fluid properties, and flow properties define what's happening. And we can set that equal to 32 mu LV rho G d squared is equal to F L over D, and I need to not write it that way, V squared over 2G. And what that gives you is a way of redescribing what's happening in terms of these friction factors. And so friction factor, laminar, equals 64 rho GD squared mu V over 32 mu L V rho GD squared V. 64 mu over rho V D, 64 over Reynolds number. So if I have a laminar flow, I can calculate that friction factor just based on the Reynolds number of the diameter, or Reynolds number based on diameter. So 64 over Reynolds number, I can make that look a little better. 64 over Reynolds number is a solution that will work for every case in laminar flow. Go ahead. Yeah, so we're going to end up, what's going to happen in the next lecture, well, in this lecture we'll sort of say, hey, everything works really well with laminar flow. Then we're going to look at the Moody diagram. And what I'm going to also try and introduce are a couple different approaches. So in the process of looking at all of these things, I did find a whole bunch of analytical solutions that might be interesting, and I'll talk about those next time. But for this lecture, yes, and for every lecture, it's correct. So I have oil, and it's flowing down or up, or flows in an inclined pipe. So it's going up. Find QV, and to check if the flow is laminar. So I have position 1, position 2. I also have here the pressures. So I have 350 kilopascals and 250 kilopascals. I have a 40-degree incline, and I have a 10-meter distance between point 1 and point 2. I'm given enough information that I can calculate the height difference or the head loss between the 2 points, because this is, okay, I'm assuming it's fully developed flow. And that's usually a safe assumption in these cases. You have to assume it, otherwise, good luck. Ooh. So if I know what the head loss is between points 1 and point 2, and I substitute all the numbers back in, the only unknown is Q. And I get Q equal to 0.0076 meters cubed per second. And all it is really a substitution back to volume over area for the head loss term. So from that, you can extract out velocity, which is equal to q divided by a, which is equal to 2.7 meters per second. Reynolds number is equal to velocity d over kinematic viscosity, and that will equal 810. So I need to check every solution I get, and you're going to get a lot of different cases where you look at different types of flows, and you're going to make some base assumption to start the whole process. You have to check and make sure it makes sense. Good. I'm sorry? Oh, sorry. It's this one, but it's just been V is equal to Q over area.
Also, it's substituting in Q?
Yeah, that's all it's doing.
And then the 128.
Sorry. Oh, okay, so the 128. So if I do this, then V is Q over area, Q over pi d squared divided by 4, and then you multiply all that stuff out, and you're going to end up with 128. Yep. And just sort of mentioning this, you really do want to be able to transmit or translate between velocity and volumetric flow rate, because you're going to have different kinds of cases that you look at. But if we check that Reynolds number, it's 810, and 810 is less than 2300, and flow is laminar. So my base assumption, just one second. So my base assumption is okay, and my result makes sense. Go ahead.
Okay, so it's like we're checking Reynolds number to see, to like confirm, okay, using that formula was okay.
Exactly. And what you're going to end up doing, this is not as interesting here, in the sense that I already know I get a solution, it's probably going to be okay. But what's going to be more interesting is in the next lecture, actually, where you really do have to go back and forth. So we'll do iterative approaches to solve through for things. Okay, same sort of thing. Very small diameter tube, liquid with density of 950 kilos per cubic meter, flows from a tank through a horizontal capillary tube. The liquid surface is 60 centimeters above the tube exit. The tube length is 30 centimeters. Diameter is 1.2 millimeters. So again, very important. Small diameters usually give you a clue that it's going to be laminar. Flow rate is 1.2 cubic centimeters per second. And this is where, where you have to worry about your units, because you've got everything in all sorts of different things. You've got kilograms per cubic meter. You've got centimeters cubed, you've got centimeters and millimeters. And you're asked to compute the liquid viscosity of the fluid, or dynamic viscosity. Yeah. All right, laminar fully developed. Oh, so P1 equals 0, P2 equals 0. So I know that that's coming out to atmosphere, and because it's coming out to atmosphere, it's zero pressure at both points, or zero gauge. And again, really important that as you solve these problems, and it's going to be true tomorrow, even though we're not covering any of this, write your units down. When you write your units down, you can see where your errors might be appearing. And things like this, where I have to convert Q from cubic centimeters per second to cubic meters per second, or area from millimeters. I got diameter as millimeters into meters squared. And finally, velocity at position 2, 1.06 meters per second. So the difference here is that this problem has quiescent fluid at the very top. Why did you? Oh, look at me. V1 is equal to 0, and I have V2 equal to 0 over here. And if I set everything up, oh, and alpha 2 is equal to 0. That's a proportionality constant to deal with the change from zero flow to laminar flow. And I have to look at where I know I gave it in one of the lectures, so I'll have to find it. So I have a head loss between the 2 points, so 0, 0, not P1, P2. So in terms of this expression at the top, that's 0, that's 0, that's 0, that's 0, and there you go. So that's why you only end up with the last sets of terms. So the height difference, you don't even, Z1, I would say, yeah, I think normally I would just say Z2, 0. So that's 0. So it ends up being Z1 minus alpha 2 V2 squared over 2G. So if you use that laminar head loss expression, you end up with, substituting the terms in, you already know what the head loss is. You can rearrange the head loss equation, and from that, you end up with HF rho g d squared over 32 LV2. And you end up with a final result of 6.4 times 10 to the minus 4 Pascal seconds. So you're just applying equations, but you have to recognize where things are going. Go ahead.
So for the length, when you do that, when you do the final calculation, it's just 30 centimeters, not 9, right? 30 centimeters is where it's fully.
Exactly. So as far as we're concerned, even though when you look in this region right here, you would see a velocity, we pretend that at the entrance is when it switches from 0 velocity into whatever it finally ends up at. So that's really important that you understand. In this course, we're not making a really big effort to look at what's happening at that entrance region. We will in the next in the third lecture in this series, where we look at entrance losses. But we aren't going to really talk about how that happens. So as far as this course is concerned, that 30 centimeters is the only thing that matters. So you have to check and make sure that you actually have a laminar flow. And you end up with a Reynolds number of 1890. And again, in this course, and I realize that's not a great way to put things, but in this course we have sort of a bright line. We say, okay, if it's below this, it's laminar. If above this, it isn't. And we sort of skip over that 2100, 2300 to 4000. We're just going to pretend it doesn't really exist. It'll be either laminar or turbulent. It will not be a combination of both. So Reynolds number based on diameter is 1890, which is less than 2300. And so we can say that that is in fact a laminar flow. Ooh. And this is where I could get myself in a little bit of trouble because I'm going to sort of go between 2300, 2100, and I can't remember where I do that changeover. Derive a formula for the time delta T for a volume V to drain and find the diameter D for water with given parameters. So you're given, again, you have two very large reservoirs, one on top of each other. It looks like an hourglass, and the hourglass is connected by a thin tube which has a diameter or a diameter of, oh, sorry, the diameter, I don't write it down. Okay, I have a length there. I have a head of water on top of it. I have a velocity of 8, or kinematic viscosity, or dense, or volume of 8 cubic centimeters. And the time to drain, okay, so time delta T, 6 seconds. Volume of fluid to drain, given the parameter, or find the parameter D for water given those. Okay. So we can say that the driving head between the top and the bottom is really the height of the water plus the length of the tube. And we're going to use a laminar head loss and substitute again that we have velocity over the delta T, which is the time it or volume over delta T. And I'm going to regret my notation. And my volume here is 8 centimeters cubed. You solve for delta T to get the general formula, and then plug in the values for water to solve for the diameter. So delta T is equal to 128 mu L total. Volume, I'm going to call that volume slash pi rho g d to the 4th, which is equal to delta T equals 128 mu L plus L volume divided by pi rho g d to the 4th. So all I'm doing is saying, look, the Q of this is just going to be a volumetric flow rate that is going to be determined from all of the properties that I have. I've got water density, all of that, and I end up with 6 seconds is equal to 128, 0, 0, 1, 0, 1, 2, 8 times 10 to the minus 6, all over pi 998, 9.81 d to the fourth, 0.12 plus 0.2 equals, or yields d, which is equal to 1.5 millimeters. Okay, yeah, so all of the terms are there. You're just missing d in this. That's your only unknown. A little bit of calculation, nothing very serious here. Really, it's just setting up the initial equation so that it works out properly. Any questions so far? All of these are applying, sorry, go ahead.
Yeah, I just wanted to ask, why did you, like, I'm just confused on the lengths, because you wrote 128 and you used L plus L, you used over pi rho, and you used power 4. Where did you get the 0.12 or 0.12 plus?
Right. So that's over here, 2 centimeters and 12 centimeters.
Okay, but the formula only had L plus L. Like
Yeah,
the 0.12 plus 0.02.
that's correct.
Is that the L? Is that loss?
That's, okay, oh, okay, wait a minute. I'm going from here to here. I'm not going to the bottom of the tank. So I'm filling the tank. And I'm pretending, I mean, where this problem sort of falls apart mostly is that I'm telling you it's draining, and as it's draining, the head is changing, but the length of the tube is the only thing staying constant. So this would, you would treat this in reality as if it's an average over which this has occurred. So it's probably better to say it was initially 4 centimeters, it ends up being 0 centimeters. At the end, I have a height, an average height during that time of 2 centimeters. It's not a great way to put it, but there you go. Okay, continuing. So there are a lot of, you're going to spend a lot of time on this. So I have SAE 50 weight oil at 20 degrees C flowing between 2 tanks. Tank 1, tank 2. I have a length between the 2 tanks of 1.6 meters, D of 5 centimeters, and the height difference is 1.2 meters. What else do I have? Fluid, SAE 50 weight oil, and this is something that you'll see a lot of. We'll do various types of oils, and we'll give you information. So for example, we'll give you the density and the viscosity. Now, in this case, because you would do all of your balances between the 2 free surfaces, 1 and 2, the only thing driving this is going to be the height difference. So in fact, what you'll see is V1 equals V2, which equals 0, and P1 equals P2, which equals 0. And we, again, when you're dealing with free surfaces, you always assume that they are just sitting there and nothing's changing with time. So I can substitute in all the expressions, and what I'll get is that I have Q, which is equal to 0.00118 meters cubed per second. So I'm going to assume always laminar flow in this part of the course. In a very small set of lectures, this lecture, that's the only thing I care about. And I get Q is a very small number, 0.00118 meters cubed per second. Now, you can do the same thing as you've done other times where you say, hey, I can write this in terms of velocity for Reynolds number or in terms of volumetric flow rate, and you're just going to have velocity divided by area. If you put all the numbers in, you end up with the second expression there. And if you do it in terms of hours, the flow rate is 4.3 cubic meters per hour, which is actually a pretty large amount or large volume over a very long time to be moving. But Reynolds number based on diameter, 32, well below the 2000 limit. Why did I? And I need to. Oh. So for flow in pipes, we have a set of equations already in place that allow us to sort of solve through for everything, and I just want to write them out correctly. So we have HF, which is FL over D, V squared over 2G. And for laminar flow, it ends up being 32 mu LV divided by rho G D squared. So you have a very comfortable set of solutions and a kind of ersatz cases that we looked at here that are going to work out really well. And in case you're wondering, the next lecture will introduce all the problems and look at different ways of solving for those problems. So let's do one last example. Oh, I did good. Why? Oh, sorry. This one is not the one I planned to do. All right, I'm actually going to okay. sorry. Sorry, I had planned to give a different set of notes, and I just realized I didn't copy them over, so I don't have my solutions here. And I don't like guessing. Dynamics. Oh. All right, I'm going to go crazy with this. Maybe I'll just go back over what I was going to cover anyways. All right, so the main point out of this, really quickly, hello, Renee. Sorry. Is we're going to spend a lot of time looking at what's happening within these piping systems, extracting out these relationships between length over diameter. And then we're going to start to look at something called a Moody diagram. And what I hope to cover in the next lecture is how to apply these ideas that there's a friction loss, things have happened, and that friction loss is something that is definable in terms of shear stress that's driving it. Friction is really associated with what's happening at the wall. And it's also measurable in the sense that if I know what the height difference is, I know what the pressure difference is, and usually I don't worry about velocity, I'm going to end up with this relationship. So if I do that for a typical pipe flow, which is circular, I'll end up with this relationship for shear at the wall times L rho GD, and then I'll end up with the Darcy-Weibach equation, which is what I now try to fit for the rest of chapter 6. And let's see what else we're going to talk about. You're going to define things in terms of head loss with respect to velocity because that's usually the only thing that's driving the flow. And sometimes you're going to have to do that in terms of volumetric flow rate. So as long as you sort of look at both of those and get comfortable with these types of approaches, the problem is that what's going to end up happening is Thursday for you guys, I'm going to start looking at the Moody diagram. And the Moody diagram is all of this for the turbulence. And over here, it ends up being 64 over Reynolds number. And at that point, we stop. And we'll continue next.